Dark matter is usually thought of as something out there. However, we will never truly understand it unless we can bring it down to Earth. If we could see dark matter, the Milky Way galaxy would look like a much different place. The familiar spiral disk, where most of the stars reside, would be shrouded by a dense haze of dark matter. A dense haze of dark matter particles. Astronomers think this dark haze is 10 times as massive as the disk and nearly 10 times as big in diameter. My dear and esteemed viewer, the universe around us is not what it appears to be. The stars make up less than 1% of its mass. All the loose gas and other forms of ordinary matter, less than 5%. Just less than 5%. The motions of this visible material reveal that it is mere flotsam on an unseen sea of unknown material. We know little about that sea. The terms we use to describe its components, dark matter and dark energy, serve mainly as expressions of our ignorance. For 70 years, astronomers have steadily gathered circumstantial evidence for the existence of dark matter, and nearly everyone accepts that it is real. However, circumstantial evidence is unsatisfying. It cannot conclusively rule out alternatives such as modified laws of physics, nor does it reveal much about the properties of the supposed material. Essentially, all we know is that dark matter clumps together, providing a gravitational anchor for galaxies and larger structures such as galaxy clusters. It almost certainly consists of a hitherto undiscovered type of elementary particle. Dark energy, despite its confusingly similar name, is a separate substance that entered the picture only in 1998. It is spread uniformly through space, exerts a negative pressure, and causes the expansion of the universe to accelerate. Ultimately, the details of these dark components will have to be filled in not by astronomy, but by particle physics. Over the past 8 years, the two disciplines have pooled their resources, coming together at meetings such as the Symposia on Sources and Detection of Dark Matter and Dark Energy in the Universe. Now, the goal among the most difficult experiments, the goal has been to find ways to detect and study dark matter using the same techniques that have been so successful for analyzing particles such as positrons and neutrinos. Rather than inferring even its presence by looking at distant objects, scientists would seek the dark matter here on Earth. The search for dark matter particles is among the most difficult experiments ever attempted in physics. The search for particles of dark energy is even less tractable and has been put aside, at least for the time being. More astronomers think the heavens are filled with dark matter, but their observations are too imprecise to provide unequivocal proof, let alone measure the detailed properties of the supposed material. Particle physicists are trying to take up the slack by building detectors to look for the dark matter as it streams through Earth. Particles of dark matter, though reluctant to interact with ordinary atoms, should still do so occasionally when such a particle ricochets off an atomic nucleus, the nucleus recoils, hits surrounding atoms, and releases energy in the form of heat or light. The real trick is to distinguish this energy released from the effects of more prosaic processes, such as radioactive decay. Such effects may account for the only reported detection of dark matter to date. Now, what kind of particle could dark matter be made of? Astronomical observation and theory provide some general clues. It cannot be protons, neutrons, or anything that was once made of protons or neutrons, such as massive stars that became black holes. According to calculations of particle synthesis during the Big Bang, such particles are simply too few in number to make up the dark matter. Those calculations have been corroborated by measurements of primordial hydrogen, helium, and lithium in the universe. Although the neutrino is heavy by normal standards, it is generally thought to be the lightest supersymmetric particle. If so, it has to be stable. If a superparticle is unstable, it must decay into two lighter superparticles, and the neutrino is already the lightest. As the name implies, the neutrino has zero charge, so it is unaffected by electromagnetic forces, such as those involving light. The hypothesized mass, stability, and neutrality of the neutrino satisfy all the requirements of cold, dark matter. The Big Bang Theory gives us an estimate of the number of neutrinos that were created within the hot primordial plasma of the cosmos. The plasma was a chaotic soup of all types of particles. No individual particles survived for long. It would quickly collide with another particle, annihilating both but producing new particles in the process. Those new particles soon collided with others in a cycle of destruction and creation. But as the universe cooled down and thinned out, the collisions became less violent, and the process ground to a halt. Let's talk about the dark wind. Like motorcyclists feeling the wind in their face, we on planet Earth are being blasted by a headwind of dark matter. The dark matter is essentially a stagnant gas. Particles move randomly but have no organized motion. And our solar system roars through this material at 220 kilometers a second. Within the solar system, Earth orbits at 30 kilometers a second. When the tilt of the orbit is taken into account, the headwind has a net velocity of 235 kilometers a second in the northern summer and 205 kilometers a second in winter. This variation distinguishes dark matter from noise, which does not change with the seasons. Let's talk about that neutrino, shall we? It's a particularly collision-shy particle, so it froze out early on. At the time, the density of the universe was still very high, so a huge number of neutrinos were produced. In fact, based on the expected neutrino mass and its low tendency to collide, the total mass in neutrinos almost exactly matches the inferred mass of dark matter in the universe. The correspondence is a strong sign that neutrinos are indeed dark matter. To detect dark matter, scientists need to know how it interacts with normal matter. Astronomers assume that it interacts only by means of gravitation, the weakest of all the known forces of nature. If that is really the case, physicists have no hope of ever detecting it. But the astronomer's assumption is probably just a convenient approximation, something that lets them describe cosmic structures without worrying about the detailed properties of the particles. Theories of supersymmetry predict that the neutrino will interact by a force stronger than gravitation, the weak nuclear force. The vast majority of neutralinos will slip through a slab of matter without interacting, but the occasional neutralino will hit an atomic nucleus. The unlucky particle will transfer a small amount of its energy to the nucleus. The improbability and feebleness of the interaction are offset by the sheer number of particles. After all, dark matter is thought to dominate the galaxy. Being dark, it was never able to lose energy by emitting radiation, so it never could agglomerate into subgalactic clumps such as stars and planets. Instead, it continues to suffuse interstellar space like a gas. Our solar system is orbiting around the center of the galaxy at 220 kilometers a second, so we're pushing through this gas at quite a clip. Researchers estimate that 1 billion dark matter particles flow through every square meter every second. 1 billion every second. So, let me talk a little bit about cryogenic detectors, such as been set up through all this sector of the galaxy. The cryogenic dark matter search are designed to measure individual phonons, or quanta of heat in a material. They operate at a temperature of about 2.5 millikelvins and use thermosistors to record the temperature rise in the various parts of the apparatus. Individual detectors have a mass of a few hundred grams, and researchers can stack a large number of detectors to reach a total mass of a few kilograms or more, thereby boosting the signal. So, with such cryogenic dark matter search devices, detectors spread throughout the galaxy, let's keep this in mind as we continue to construct an image and understanding in our mind of what this material is that dominates the galaxy. So, the cryogenic detector, the most advanced project involving this detector, is essentially above the techniques ever introduced thus far in this search for this nefariously elusive structure of the universe that makes up the entire universe. It's like, how can something so ubiquitous and so prevalent and comprising 99% of the universe be so little understood? How? It's just bewildering. And the confirmation of supersymmetry would imply a vast number of new particles waiting to be discovered. So it's like we don't even have, it's like, what do we even know as humans? Yet we're the most smug, self-satisfied, I don't know, forms of life in this sector of the universe. However, if detectors can spot particles of dark matter, such as I mentioned, the cryogenic detectors that spread throughout this sector of the universe, particle accelerators such as CERN's Large Hadron Collider near Geneva might be able to recreate them and conduct controlled experiments. The confirmation of supersymmetry would imply a vast number of new particles waiting to be discovered, and would lend support to string theory, in which supersymmetry plays an integral role. The greatest mystery in modern astrophysics may soon be solved. And I give you my assurances, my dear and esteemed viewer, that if you hit that subscribe button, you will be on the forefront of this cutting-edge gnosis, where you will be brought this latest developments in astrophysics. Truly exciting times, folks. Truly exciting times.
Namaste, namaskaram.